Okay. Well, even if we are a bit earlier, I guess we can still start now.
Yes.
I will give you the co-host, right? Now you are co-host. Okay. And the floor is yours.
Thank you. I believe you can see now my screen.
Yes, it's okay.
Great. Hello, many greetings from Porto. My name is Biri, and I'm here to present our work. I work as a researcher student in this project, which is called CORE, and this is the main goal is to have a rehabilitation series game. So I would like to start with providing some context and motivation. As we all know, in today's world, augmented reality, virtual reality, or let's put it in all immersive technologies, has been already gone much more beyond than just being a game, more than being an entertainment item. And they are widely used in many different application areas, such as education, training, medical training, for instance, or rehabilitation, construction, architectures. And due to the challenges regarding the tracking or interaction, also it is still a very attractive domain for many researchers. And it has the, besides these challenges, it has the potential that comes with the applications itself. And the main key is the immersion. The immersion is basically to have a sensation, a mental sensation of an engagement that makes us believe, our brains believe, or let's say convinced that there is a object here, the same environment with me, and it is possible for me to interact with it, because I will be believing it exists in runtime and I can interact with it. And this will be, if we would be focused more in augmented reality more than the others, such as virtual reality, because in virtual reality, it is much more easier to have this immersion sensation. But in augmented reality, we have to align very, very correctly the virtual object into our real world, because augmented reality refers this actually. To do this, we have to make a transformation between our real world coordinate system and the virtual world coordinate system that the user observes from a display. And this process has been called as 3D reconstructions or registration. And this is the main aim for us to do it. And this is possible only if we can track the user's point of view, or we can call it like camera position pose, or the head pose. Let's put it that way. When I say pose, meaning position and the rotation of the user. We have to find this out to have the best of the location of the user in the real and the virtual world. And in the state of the art, there are many applications and many researchers has been investigating this, mainly focusing on the computer vision based system. And when I say computer vision based system, mostly focusing on marker based system and the markerless based system. Both has the advantages and the disadvantages, such as marker based system are using identical markers, and they are easily identified in a natural environment, since they have some specific properties. But even though they are fast and they don't demand many computational power, we have to be tight to look to certain markers. Besides this, in markerless tracking system, we don't have to be looking this direction to the markers, because we can have the feature of the natural environment. And besides that, these are focusing on the RGB data. Some researchers investigated what if we use the depth information by using a depth, for instance, Kinect camera sensor, and they found out the lightning conditions, it's providing more better results with different lighting conditions, since it relies on the depth information as well. And besides these computer vision based systems, there are some other tracking approaches, such as using the inertial sensor based tracking approaches. And this provides us very fast and robust response in very fast motions, which is a drawback in computer vision systems, since they require computational power. And this is a good thing in the sensor inertial based system. Nevertheless, they have some drawbacks in the drift and the electromagnetic noise. They have the sensitive. And to make out of the best of what we have all these applications, all these approaches, as many other researchers, we would like to follow a hybrid approach. So our setup has consists of circular markers. We are also following the marker-based system. We have a Microsoft Kinect as an external depth camera. We are using a server computer running Unity application. We are also using Unity as the game engine. And we have the head-mounted device. We are using our smartphone, Android smartphone, as the display, VR display. Here we can see our application architecture. As I told, this is a rehabilitation series game. So the user is asked to perform penalty kicks, even though it is not referred in the paper, because it's only focusing on tracking the head pose. But actually the main goal is to have a rehabilitation game with penalty kicks. So because of that, we are tracking the joint of the foot of the user by using Kinect, and also the head joint. So we have here mainly two blocks with the Kinect sensor, and on the other hand, we have the head-mounted device, which is our smartphone actually. And we have basically three different sources of information for the head pose. From the Kinect sensor, we gather the full pose of the head, meaning position and the rotation, and all the rotations are represented in quaternions. And gyroscope-based rotation estimator, we are using the phone inertial sensor system to have the rotation, and we use the camera. What we do here, we are tracking the markers by using Vicon marker localization system, and we use the PMP algorithm in order to make the reconstruction between 2D image coordinate system and the 3D defined coordinate system, which is defining our real physical world. And out of this transformation matrix that we calculate with PMP algorithm, we calculate the camera pose into the virtual world. And we make all these different source of information, we combine and we fusion all this information in order to have as an output quaternion in rotation and the position. Our inputs in measurement vector is inertial sensors from quaternion and the angular velocity, and the quaternion from our phone first-person camera, quaternion from external depth camera in Kinect in this case, and position from the first-person camera and the position from the Kinect. We made a preliminary experimental study in order to compare the PMP result, which relies on marker-based vision system, vision-based system, and we compared it with the AKF, which is the extended Kalman filter. In order to ensure the positions located well, instead of having the user there in a point, we use the tripod with the phone, and we acquired 56 data of the estimation, head pose estimation between the two layers with different heights and with the various angles, such as aligned with the markers and +5 and -5 pitch, yaw, and roll. And here we have the results, RMS error, and we can see that even though AKF performs better in X and Y, we can see overall PNP results better than AKF. We could say this might happen because of the inertial system, because of the drifts and the electromagnetic noise. And this is not a big surprise, even though we knew expecting the marker based vision-based tracking system are already providing good, but the main limitation was we have to be dynamically moving, and we cannot all the time look into the markers, and we need to fastly move, especially such a game in a penalty game. To point out this problem, we made another experiment where this time the user is wearing the head-mounted device, and he is asked to rotate his hand to up to a point where the markers are not available anymore. And we can see that in this chart, the output results in rotation in quaternion values. And you can see the continuous line represents the output from the PNP, and the dashed line represents the output of the AKF. And we can see as a conclusion, the AKF fills the gap or assists the PNP whenever the marker based tracking system is not available, which happens many times in any dynamic augmented reality application. And I would like to show a video from our project. As we talk the conclusions, we can observe that we can fill the gap between when there is no available marker tracking system, but still we would like to handle the occlusion problem and improve better performance with the extended Kalman filter. And besides, we would like to merge as me being soon will be a PhD candidate in robotics, and we would like to merge augmented reality in human-robot interaction with our team. So thank you so much for listening.
Thanks a lot for your presentation. So any question in the audience? No, we don't have in the chat. So myself, I was interested in knowing a bit more like how you would scale your solution. So you are, for example, in the case of patient rehabilitation, you mean that that Kinect is not so expensive, so they could maybe after integrate some of your results, because this is the assumption is that devices like Kinect are not too expensive, and then after could also be used in patient settings, and then no more dedicated hardware is needed. So is it one of the goals of your research to try to use on-the-shelf kind of products?
Exactly. This was one of the main goals, because even though the commercial VR systems are really, really good, but they are really expensive, but we only need this printable markers and for Vicon and the Kinect, okay, maybe. But besides that, it's just a smartphone, Android smartphone, and I think if we compare, it's much more cheap.
Okay, and then in this project, so it's funded by the European Union, right? Is it H2020? Is it an H2020 project now?
Yes. Yes.
Yes. Okay. So are there plans for some production, like commercial outcomes of it, of this work, or?
This is, yes, there is, but for now this is research domain still. But yes, we are thinking to improve it much more better and has a commercial. And it's not only for rehabilitation. We have like two domain. One is for rehabilitation, the one I presented, and there's another for the education, to make a game and make the students around I think 11, 12 years old, make them learn the subjects in the school, whatever they have, in a game application, basically two parts. And there is another part of the project, but again, not very connected, but it is to having the gesture recognition of the supports, for instance, football players, and we have a short with the sensors, and we are thinking to integrate this into the augmented reality, this project. And so basically we have a different project, but we are trying to merge them all together to have a better impact.
There was a question in the chat now. It's can this approach work for integrated virtual reality HMD display, such as Oculus Quest?
Can I see it? I am trying to, sorry.
Yeah, so did they ask you if this approach can work with Oculus Quest, for example? Maybe it's a specific head-mounted display. I guess so, no?
I'm just trying to see the question chats. Okay, no.
I think you should. Yeah, you should be able to see it. But
can you repeat the question? Sorry.
Can this approach work for integrated virtual reality head-mounted display, such as Oculus Quest?
Such as?
Oculus Quest, you know, the one.
Can I support virtual reality such as Oculus Rift? This is
Yes, yes. Can it work with other? I would think it's yes. I mean, your approach can be used with other head-mounted displays, right?
yeah. If it's the question, so I'm sorry, I couldn't see the question. And but if it's the question, if we can able to integrate our solution to other hardware systems such as
Yes, yeah. So such as Oculus Quest. I don't know. Maybe it's a specific
yes, yes.
one.
This is actually this is true. Even we can use their because they are commercial and they are really precisely providing good results, especially in head pose tracking. But we can use this as another source of information in the sensor fusion. And since they already have very good precise localization system.
Okay, thanks a lot for your presentation. And I think now we are having the last presentation before the break, which is so pen shaft, enabling pen shaft detection and interactions for touch screens. And the presenter is John-Louis Sun, I think.
Yes.
Yes. Okay, so I will share. I will give you the role of co-host. Okay, do you see the
Yes.
Yes.
Yes. Can you see my screen?
Yes, so you can share screen now.
Okay.
We see it.
Okay. Thank you, Jean-Marc. Hello, everyone. My name is Junwei Sun. I am a researcher at Huawei Human Machine Interaction Lab in Toronto, Canada. So today I'm going to present this work, pen shaft enabling pen shaft detection and interaction for touch screens. So this is a collaborative work between Huawei, University of Waterloo, and University of Manitoba. So, like as mentioned in the title, so the pen shaft here is actually a battery device, so a battery-free device, low-cost solution that turns a pen shaft into an input device that can be used on a capacitive screen. So basically what we did here is to apply conductive materials around the pen shaft. As you can see in the figure, we simply apply coppers around the shaft of the pen. And then, so that this pen shaft can be used on capacitive touchscreen. I mean, here it shows some previous work about pen-related work or pen-related research. Some of the research use pen and touch solution for interacting on touch screen. Some of them use the pen even in AR and VR, and in some cases they apply some sensing material around the pen shaft for posture and grip detection. And so the system is able to tell in which grip the user is holding the pen. I mean, there are some other work that apply a different kind of feedback on the pen. But in those pen-related research, I mean, most of them utilize the pen tip for interaction. I mean, for these kind of pen and touch solutions. Even some of them use the pen shaft for detecting the pen grip. I mean, they are not directly using the pen shaft itself for interaction. They use the pen tip for actually interacting with the touchscreen. So Basically, what we did is to directly use the pen shaft itself for interaction. And here are some capacitive sensing techniques, because like us, there are some other, previous work that presents tangible devices that can be used on a capacitive screen. For example, toolstone, Conte. Basically, in these cases, the user can hold the device in any way they want. They can basically use each face, each surface, each edge, and each corner of the device, and then different type of input will be allowed. But none of these capacitive sensing technologies is in the shape of a pen. I mean, the Conte is in the shape of a Conte crayon, but still it's not in the shape of the pen. So what we would like to do is to basically have a capacitive sensing device directly on the pen shaft. And so basically this video shows how we make the pen shaft. It's like really simple. The video is 4x speed. So basically we just find a normal cuboid shaped pen, and then we simply apply copper tapes around the pen, around the pen shaft. As you can see, this is a 1 minute video, which means that it takes about 4 or 5 minutes just to make this device, and it's really simple. So once we finish making this device, as you can see in the video later, we can just simply grab a touchscreen and use it on a touchscreen. And here it is. So basically, as you can see, it's like really simple to make such a device. So basically, this is a little bit of technical detail of like how the pen shaft works. So in this configuration, we put basically 6 contact points around the pen shaft. There's PA to PC, and then P1 to P3. And also in this case, PA, PB, PC, as you can see here, they're not connected to each other. They're individual. They are independent from each other. P1 and P2 and P3, they are connected by another copper tape. So whenever the user holds a pen shaft on the screen, they hold the area where, which is from PA to PC P1 to P3, right? And since P1 and P3 are all connected, once the user holds the pen in this area, the screen will detect 3 contact points. And since we make D1, the distance between P1 and P2, and D2 different, the system is able to tell in which direction the pen is held. And also here, PA, PB, and PC, they provide the force contact points. So if the user is holding on this end of the pen and they press or hold either PA or PB or PC, therefore a force contact point will be detected. So this force contact point can be used as buttons. So we did some user study to evaluate the performance of the pen shaft, basically. And we have 6 tasks. And here's the video that shows that. So this is the stationary task where only the last three contact points is used. This is the dragging task. This is the rotation task where the user can rotate the whole pen shaft to rotate a target on the screen. This is the clicking the button, a button click task. This is a button hold. So the user hold the button for 2 seconds. This is a sliding task where the user have to slide. So basically the last one was to slide from one button to another button. So yeah, so here is the result of the study. I mean, we measured the error rate of each one of the 6 tasks, and we also conducted a questionnaire to ask the users' feedback about all these 6 tasks. So as you can see, in terms of fatigue, comfort, ease of use, speed, accuracy, they all achieve about above average ratings for all tasks. And in terms of error rate, there's on average a 5% error rate in terms of the task. And we did some individual analysis for some interesting tasks. So as you can see, the rotation is the rating for rotation is not that great, but we believe that is because the user have to basically rotate the entire punch shaft, and the conditions include rotating the punch shaft in 30 degrees, 60 degrees, 90 degrees, and 120 degrees. So it's not surprising that the 120-degree rotation is ranked the last and performed the worst, because the user had to rotate the entire punch shaft for 120 degrees. It's not easy to do. In terms of sliding, we found some interesting result, like the so the B2C button slide is ranked the highest, and the C2I is ranked the lowest. Basically, the B2C, the button B and button C are closer to the users to the end of the pen. They're like the coaster buttons, and then the B2C is basically a swipe down. It's easy to use, but C2A is from the closest button slide on to the furthest button. So it's like the user had to slide up. So that was the least favorable one. But overall, we achieved only like 5% error rate, and we got above average ratings for all the tasks. And in terms of applications, the pen shaft can be used in all kinds of applications, such as screen splitting, coloring application, 2D object manipulation, a drawing application, image cropping, and all of that. I'm going to show videos of each one of the applications. So this one is a split screen using pen shaft drag. The user simply have to place a pen shaft on the screen, and then they can conduct a split screen. Basically, the edge of the splitting of the screen will be exactly where the pen shaft is. So this one is a coloring application. So basically, as you can see, like there are different colors in the screen, and then with one single swipe of the pen shaft, the user is able to erase a single color. So here they choose color blue, and with a single swipe, the entire blue color is gone. They do some coloring. With a single swipe, the color red is gone, or pink. With another single swipe, the color green and yellow is gone. So this video shows that the pen shaft can be used in a 2D objects manipulation task. So the user can select an object, use a pen shaft to translate, rotate, and scale the 2D object. So here it shows the contact point. So by simply moving the pen shaft without using the button, the user can achieve translation and rotation. And with the help of the button, they can use scaling as well. So they drag the pen shaft to translate it, use the button to scale it, rotate the pen shaft to rotate the 2D object. The next one is to crop a 2D image by placing the pen shaft on it. So basically, this is pretty straightforward. Wherever the pen shaft is placed on the screen, we use that line or that edge to split, to crop an image. This last one is a drawing application. Basically, as you can see here, as you can see here, the user is able to place the pen shaft on the screen, and the menu will show up. Basically, it has 3 options, right? And then by pressing the buttons, button A, button B, and button C, they can switch the mode. They can choose whether to use a brush or eraser or draw. They can just, turn the drawing application to different mode. They choose a brush. Now they choose an eraser. They go to the draw applications. They can change the attributes of the stroke. Basically, they're able to change the color, the thickness, the transparency of the stroke. And here, as you can see, as you can see, they can switch between a thin stroke and a thick stroke. And here, with rotation of the pen shaft, they can change the value of the RGB of the color. Basically, they can change the color of the stroke. Now they chose the red attribute, and by rotating the pen shaft, they can change the scale of red in here. And once they go back, they can go to other attributes, as you can see, for example, transparency, right? So with the help of pen shaft, there's no UI needed. Basically, the UI is hidden in the pen shaft. And then once the user places the pen shaft on screen, the UI will show up. They can use the button on the pen shaft for changing the mode, or basically use the button as a hotkey in this drawing application. So here's a little takeaways. Here's a few takeaways of my talk. So the pen shaft is a battery-free augmentation for passive capacitive pens. Our study showed that it achieved 95% recognition rate. And in terms of the, basically the user liked using the pen shaft as the input device on the touch screen. And the pen shaft support a wide range of pen-based interactions, including the ability to engage with hotkeys, menus, content manipulation directly with the pen shaft. And in the future, we plan to, there are a few things we plan to do in the future. One of them is to tackle the fat pen problem. So as we all know, there's when you are using a touch screen, either with a finger or with any other device, there's this fat finger problem. But with the pen shaft, obviously the pen shaft is gonna obscure some content on the screen. So we're gonna to tackle the fat pen problem is one of the goals. And also we would like to examine the ergonomics of the pen shaft. So as you can see, we made a really simple configuration. We just find a normal cuboid shaped pen and then simply applied cover tape around it. The whole process takes like 4 or 5 minutes to make this pen. But maybe in the future we will examine the ergonomics of the pen. So how to make the pen shaft, more comfortable to use. And then we would like to investigate the transition costs between the traditional pen grip and pen shaft. Basically, the application itself showed how the pen shaft can be used, but sometimes the user need to transition between the pen tip and the pen shaft. So we would like to examine the transition cost. that's it all for my presentation. Thank you for your attention, and I'm open to questions.
Thanks for your presentation. So there is no question in the chat. You can ask if you want your question. I have a few questions. Yes, you mentioned that, okay, there is a fat pen problem, but also this kind of pens can sometimes can be lost. And then maybe an application might need to go back to the traditional way of interaction. So what do you think of this problem? And do you believe that the such pens can be can grow and be more adopted because they would have more features than traditional pens, or that maybe it will be only for specific applications?
Yes, thank you for the question. I think the point of the pen shaft, one of the point of the pen shaft is that it provides semantical meaning when in terms of interaction. So basically, if you think about, if you want to crop an image or if you want to split the screen, you see this line. So basically, you require this line kind of input. So with the splitting of the screen, you would like to specify where the edge of the screen is. That's a line. And then in terms of the cropping of the image, again, you want to specify a line of the edge of the image. So basically, a pen shaft is a line. It has some semantic meaning. That's why it's different from the traditional touch or a pen tip, because with the pen tip, you're using the pen tip to drag or draw a line. So I think the pen shaft itself is more straightforward in terms of that. It has some semantic meaning, and also, like I said, one of the advantage of the pen shaft is that it reduces the amount of UI on the screen. Basically, once imagine you are in this drawing application, and of course, I mean the traditional drawing application, they're like a bunch of UI, and you can just choose to have. You can use the pen tip to select, and when you're drawing, maybe they can be hidden or stuff. But still, we have this potential of getting rid of UI entirely. Basically, we can hide the UI in term right on the pen shaft. So whenever the user would like to switch color or switch to a different mode, they can basically simply just place a pen shaft on the screen, and then the UI will show, the menu will show. So basically, it's a trade-off. We understand that it's a trade-off between having the UI all the time versus not having the UI, giving the user nice blank space to draw, but still hiding the UI in the pen shaft, and the user can use it whenever they want. So yeah, we believe that the pen shaft has some potential to be more adapted. I mean, after all, our current configuration is really simple. It only takes 4 or 5 minutes to make it. But we believe the idea of using the pen shaft can be adapted more.
In terms of new interfaces with augmented reality, would you see, with no screen to interact, but actually maybe the hands and so do you see an adaptation of this kind of device, even if there is no screen? I mean, to put it on, maybe.
Well, that would be hard because, like I said, so this is a capacitive sensing technology. Basically, the idea is to train I mean, we apply conductive materials around the pen shaft so that they can drain current from the screen, and you know, so that it can be, you know, replace the fingertip or, you know, active pen. So yeah, it requires a capacitive screen for it to work. But I think it has some potential to for some ice-free expert mode. So we also mentioned this paper, like so if so with the pen tip and with the fingertip itself, it's really hard to do it ice-free. But with the pen shaft, I mean, the user simply have to hold the end of the pen, and then you know, the user knows where the 3 button is, then it's able to perform some ice-free interaction, which is, I think is really cool, because once they memorize once they hold the end of the pen and then memorize the whereabouts of the 3 buttons, then it's able, like, they are able to perform ice-free interaction. So I think this is also an advantage that, you know, the pen tip or even the finger interaction, they don't afford.
There are some augmented reality. I remember that you artists can draw in 3D. You know, like okay, they have they see in 3D around them, and then they can draw paintings, but in 3D around them using hands recognition. So there might be, but then it would be not it would not be capacitive, but it would be like another style of recognition of the place of the pen or the position of the pen.
Yeah, yeah, it is exactly like it requires a capacitive screen to work, but for AR and VR, I think to track the position of the pen, it requires some, you know, either computer vision or some, you know, additional technologies. Yeah.
Okay, thanks for your presentation.
Thank you.
Thank you so much. If there are no other question, then I think most of the long presentations have been done. There was a break at 3, and then now we have a bit earlier. Anyway, so we're going to have a around 1 hour break, and then we'll start again at 5:30 Geneva time for shorter presentations. So this will be about shorter contributions, including posters that have been after published as a short paper, because we couldn't really, do a poster session remotely. So we do a break. You can either stay here. I will stop the recording. Actually, then I will restart it later because I think there is a timeout. So